page sizes async method. And let's include the private access modifier within the SumPageSizes async method's method definition. The next thing we need to modify in our example for the SumPageSizes async method is where the code writes text to the console screen. Our output will be added to the list view control that we named LVW output. So let's replace the console.write methods with a call to our private method named addListItem. We can remove the \n character sequences from the relevant text because we don't need a line feed, due to the fact that we are adding each item of text as its own item within the list view control. Let's read the brief description of this method provided within the relevant Microsoft web page. The method starts by instantiating the starting of a stopwatch. It then loops through each URL in the s_URL list and calls process URL async. With each iteration, the s_cts.token is passed into the process URL async method, and the code returns a generic task where tResult is an integer. So within the relevant Microsoft web page, let's look at the section entitled Add Process Method. So the first line in this section reads, add the following process URL async method below the SumPageSizes async method. So let's copy the process URL async method to our clipboards like this and appropriately paste it within the mainpage.xaml.cs file like this. Let's remove the static keyword from the process URL async method's method definition. Let's include the private access modifier within the process URL async method's method definition. Let's replace the console.write method with the addListItem method, like this. And if you'll remember, before we started implementing this example, I spoke about one of the prerequisites for creating this code example. The prerequisite being the installation of the .NET 5 SDK. So this is the only line of code that doesn't work if we do not have the .NET 5 SDK installed, and if we are running this example using the .NET Core 3.1 runtime. So if you are running this project using the .NET Core 3.1 runtime, simply remove the argument named token from the line of code that calls the response.content.readAsByteArray async method. So let me just say that it is preferable to pass in the token argument to this method, but if you don't wish to install the .NET 5 SDK at this time, we are still able to run the code by removing the token argument. This is not ideal, but we are still able to gain an understanding of the cancellation token source object and how we are able to cancel one or more asynchronous operations using one cancel token source object. Let's read the explanation of this method in the relevant Microsoft web page. For any given URL, the method will use the client instance provided to get the response as a byte array. The cancellation token instance is passed into the HTTP client.getAsync and HTTP content.readAsByteArray async methods. The token is used to register for requested cancellation. The length is returned after the URL and length is written to the console. So obviously where it says the URL and length is written to the console, in our example, we are instead adding the relevant text to our list view control. Okay, so let's implement the code for the button that invokes the download operations. Let's go to our designer surface and double-click on the button labeled Download Content. Let's implement the code that calls the awaitable SumPageSizes async method to perform the downloading of the relevant content, the calculation of the size of the content, as well as the outputting of the relevant information about the content to our list view control. So in order to call this method asynchronously, we need to include the await operator. We also need to include the async modifier within the method definition of the relevant button click event handler. Let's implement the cancellation functionality. Let's go to our designer surface and double-click on the button marked Cancel Download. Within the relevant button click event handler, let's implement the cancellation functionality. To add the operation, we can simply call the cancel method on the relevant cancellation token source object, like this. Okay, let's run the code. Firstly, let's demonstrate what happens when we click the Download Content button. So let's allow the operations to complete so we can see what happens when we don't cancel the operations. We can see that the appropriate output is presented to us as each operation completes. When the content for a particular web page has been downloaded, the web page URL followed by the number of bytes downloaded is presented on our list view control. And then once all the operations have completed, we are presented with the total number of bytes downloaded as well as the time that has elapsed between the time when we started to download the content and the time that the relevant download operations completed. Great! So let's run the code again. Let's click the Download Content button, and we are presented with the relevant output in our list view control as expected. Right, let's see what happens when we press the Cancel button. And a runtime error occurs. So in order to handle the cancellation operation appropriately, we need to handle a particular type of exception. So when the cancel method is called while the asynchronous operations are running, an exception of type task cancelled exception is thrown. So we can simply include our code that calls the sum page sizes async method within try-catch code like this, and handle the task cancelled exception appropriately. So we could access the thrown exception object to access details about the exception, but in this case, we only want to output status information to the user that the operations have been cancelled. So let's do this. Let's simply add the literal text, download operations cancelled. So remember, we are passing a token object as an argument to the getAsync method here in the process URL async method. The process URL async method is called within a loop from within the sum page sizes async method. This token object allows us to trigger a cancellation of all running asynchronous tasks that reference this token object. When the cancel method is invoked on the relevant cancellation token source object, an exception of type task cancelled exception is thrown, and we can appropriately handle this exception in our code. Right, let's run the code. So let's click the Download Content button, and we are presented with the relevant output as expected. So let's see what happens when we cancel these operations. And there we have it. The task cancelled exception is thrown when the cancel method on the cancellation token source object is invoked, and we are handling the thrown exception in our custom way, i.e., in a way that suits our application. So we can see the output text, download operations cancelled, which is an expected result. Okay, so we are also able to automatically cancel the operations after a predefined duration of time. So let's say we wanted our download operations to be cancelled if they haven't completed within a specific time duration. The way we can do this is by calling the cancel after method on the relevant cancellation token source object. We can call this method before the relevant operations are invoked, like this. We need to pass in the duration of time in milliseconds to the cancel after method. This number represents the time elapsed from the moment the relevant operations are invoked. So let's specify 3,500 milliseconds or 3.5 seconds. Let's run the code. And you can see that after 3.5 seconds, the relevant operations are automatically cancelled. So you can see how this functionality can be useful when we want to automatically cancel an operation or operations after a specified amount of time. Great! For further information about asynchronous programming in C#, I recommend reading relevant content provided in the Microsoft Docs. So to summarize, in this video series, we looked at Microsoft's recommended approach for implementing code to run an operation or multiple operations asynchronously, namely the task-based asynchronous pattern. We discussed that running certain relatively long-running CPU blocking operations can adversely affect the performance of our applications. To alleviate these negative effects on user experience, UX, we can run these relatively long-running CPU blocking operations asynchronously. In order to implement the asynchronous code correctly, we first need to know the nature of the operations that we wish to run asynchronously. We need to first ask the question, is the relevant operation a CPU-bound operation, or is the relevant operation an I/O-bound operation? In the first part of this video series, we focused on running I/O-bound operations asynchronously using the async modifier, the await operator, and the task or generic task object. In the second part of this video series, we looked at running CPU-bound operations asynchronously using the task.run method to run operations on background threads. We also looked at the task.waitAll method. In the third part of this video series, we looked at best practices when implementing operations in C# to run asynchronously. We also looked at the task.whenAll method and how it differs from the task.waitAll method. In this video, which is the final part of this video series, we looked at how we can provide the user with the ability to cancel one or more running asynchronous operations before the relevant operations have completed using one cancellation token source object. We also demonstrated how we can automate the cancellation of running asynchronous operations after a specified amount of time by calling the cancel after method on the relevant cancellation token source object. I hope you have enjoyed the final video in this video series on asynchronous programming in C#. The next topic in this advanced C# course will be LINQ, Language Integrated Query. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from this video, please hit the like button. It will be greatly appreciated. Please feel free to share any videos released from this channel with anyone you feel may benefit from their content. I really enjoy reading your comments, so please feel free to share your thoughts with me in the comment section. As always, the code in this tutorial can be downloaded from GitHub. A link to the relevant GitHub repository has been included below in the description. Hi and welcome to the first part of a video series on LINQ. This video is also the first part of the 7th tutorial in an advanced C# course. Later in this tutorial, we'll look at a code example to help with our understanding of LINQ. But let's first answer the question, what is LINQ? LINQ stands for Language Integrated Query. LINQ is defined in the Microsoft Docs as the name for a set of technologies based on the integration of query capabilities directly into the C# language. LINQ was originally released as a major part of .NET Framework 3.5 in 2007. Here is a paragraph from the Microsoft Docs which provides an excellent overview of what LINQ is. Language Integrated Query, LINQ, is the name for a set of technologies based on the integration of query capabilities directly into the C# language. Traditionally, queries against data are expressed as simple strings without type checking at compile time or IntelliSense support. Furthermore, you have to learn a different query language for each type of data source: SQL databases, XML documents, various web services, and so on. With LINQ, a query is a first-class language construct, just like classes, methods, events. You write queries against strongly typed collections of objects by using language keywords and familiar operators. The LINQ family of technologies provides a consistent query experience for objects, LINQ to objects, relational databases linked to SQL, and XML, LINQ to XML. Note that you can write LINQ queries in C# for SQL Server databases, XML documents, ADO.NET datasets, and any collection of objects that support the IEnumerable interface or the generic IEnumerable interface. So, for example, you can perform LINQ queries against collection types like an array, generic list, generic dictionary, generic queue, generic stack, etc. Basically, any collection type that implements the IEnumerable interface or the generic IEnumerable interface. LINQ support is also provided by third parties for many web services and other database implementations. You can create custom providers using iQueryable. Custom providers will not be discussed in detail in this video series. If you would like to learn more about implementing your own custom provider, please navigate to this URL. In this video series, we'll primarily focus on LINQ to objects and LINQ to entities. LINQ to entities provides language-integrated query LINQ support that enables developers to write queries against the Entity Framework conceptual model using either Visual Basic or Visual C#. So, Entity Framework Core is a modern object database mapper for .NET. It supports LINQ queries, change tracking, updates, and schema migrations. Entity Framework Core, or EF Core, can be used to work with many databases, including SQL databases, on-premises and Azure, SQLite, MySQL, Postgres, and Azure Cosmos DB. In this video series, we won't look at LINQ to dataset or LINQ to XML. Please navigate to this URL for more information on LINQ to dataset, and please navigate to this URL for more information on LINQ to XML. To get started with LINQ, in this video we'll focus on LINQ to objects so that we can first get a basic idea of what the implementation of LINQ looks like in code and how it can be used for querying C# collections. So in the spirit of cross-platform development, I've decided to demonstrate this code example on my Mac platform using Visual Studio 2019 for Mac Community Edition. If you have a Mac platform and wish to follow along on your Mac and you don't yet have Visual Studio installed, you are able to download and install Visual Studio Community Edition 2019 free of charge from this location. All links mentioned in this video are available below in the description. If you are using a Windows OS, please don't let the fact that I'm using a Mac platform put you off following along with this tutorial. In terms of the code example that we'll create in this video, the coding experience using Visual Studio for Mac is almost exactly the same as the coding experience using Visual Studio for Windows, so this should not be a barrier for a learner to follow along with this demonstration. If you haven't yet installed Visual Studio 2019 on your Windows platform, please view a video created by this channel which provides a guide to installing Visual Studio 2019 Community Edition free of charge. So firstly, let's create a .NET Core console application. Let's name this project the Pretend Company application. Before we write calling client code in the main method, we are going to add two standard library projects. Let's first add a standard library project named TCP Data. Let's then add another standard library project named TCP Extensions. So let's now go to our project that we named TCP Data. Let's delete the class that has been automatically generated for the TCP Data project. Let's add a new class named Employee. Let's add 6 auto-implemented properties to the Employee class. ID as int, first name as string, last name as string, annual salary as decimal, isManager as boolean, and lastly, department ID as int. Let's add another class to the TCP Data project. Let's name this class Department. Let's add 3 auto-implemented properties to our department class. ID as int, short name as string, and long name as string. Let's add a class named Data to our TCP Data project. Let's make this class a static class. So let's add 2 public static methods to the data class. Let's first create a static method named getEmployees, which returns a generic list strongly typed as employee. Let's ensure that we include the appropriate using directive for the use of generic list objects at the top of our code editor. So let's include a using directive to the system.collections.generic namespace, like this. Let's write the code to add some made-up employee records to a generic list that is strongly typed with the user-defined type employee. Let's write code to return the list of employee records to the calling client code. Let's add another static method, and let's name this method getDepartments. This method also returns a generic list object, but this generic list object is strongly typed as department. Let's write the code to add some made-up department records to a generic list that is strongly typed with the user-defined type department. let's write code to return the list of department records to the calling client code. So as you can see, the getEmployees method returns a list of employee records, and the getDepartments method returns a list of department records. So in order to gain an understanding for how LINQ works, let's ensure that we properly understand two fundamental concepts, i.e. the concept of extension methods and the concept of Lambda expressions. So let's go to our TCP extensions project. Let's delete the class that was auto-generated by Visual Studio when we created the project. Let's add a class named extension. So in order for our extension method to work, we must make the extension class a static class. So we are going to add a method named filter. The idea here is we want a way where we can extend the functionality of any generic list that is strongly typed with any C# data type, including user-defined types. We can achieve this by creating our own extension method. So for example, if we want to filter employee records by criteria that we are able to specify through a Lambda expression on a generic list that is strongly typed as employee, we can do this through our filter extension method. This will be demonstrated in the calling client code in a bit. So how do we create our own custom extension method? So I'll first create the method signature for the filter extension method. First, notice that our method, like the class in which it resides, must be static, which is achieved by including the static keyword in the relevant extension method's method signature. So if we look at the first parameter in the filter method's method signature, we can see that we are using the this keyword preceding the data type of the first parameter, which is a generic list of type T. The this keyword in this context indicates to the compiler that the relevant method can be called on an object of the data type of the relevant parameter. In this example, that is a generic list which contains a type T placeholder. As we know from the video series on C# generics, a developer is able to pass a data type argument to the parameter of type T, which can be any C# data type, including user-defined types. The data type specified will be chosen depending on the requirement that needs to be met by the calling client code. We'll demonstrate the consumption of client-side code for the filter extension method in a bit. So let's look at the second parameter, which is of the delegate type func. For more information about the func delegate type, please view a video created by this channel on this topic. A link to this video is available below in the description. The first data type parameter passed to the func delegate type represents the first data type of the first parameter of the method referenced by the relevant argument passed into this parameter. The last parameter in the func delegate type definition is the return type of the method referenced by the argument passed into this parameter. So the first parameter passed into the func delegate is of type T, and the second parameter is of type bool. Note that a predicate delegate type can be used to define method definitions for a method that returns a Boolean value. So we could replace the func delegate type with a predicate delegate type. Let's use the func delegate type, but please note that we could also achieve the same end using the predicate delegate type. And as you can see, this method will return a list of objects of type T to the calling client code. So let's complete the logic for this method. Let's implement the code for the filter method. So basically, we are looping through the list on which the filter extension method is invoked. We are then adding its elements to a new generic list, also of type T. Whether or not we add this list item is based on the Boolean value returned by a method reference passed into the second parameter of the filter method. So the relevant method reference is stored in the argument passed to the parameter named func. As you can see, the method that the variable named func references accepts an argument of type T. So we are passing in each item stored in the calling client's list, which is the generic list on which calling client code will invoke the filter extension method. If the method that the func variable references returns true, the item stored in the iterated list is added to a new list. We then return the new list containing the filtered items to the calling client code. So this effectively means that the calling client code is able to use our filter method to filter any generic list based on a method created in the calling client code. This method created in the calling client code will contain the logic for filtering the relevant generic list. A reference to this method will be passed into the second parameter of our filter extension method and must adhere to the method definition represented in the second parameter of the filter method, i.e. the definition represented in the func delegate type. So we are now going to implement the calling client code, and you'll see that the method passed into the second parameter of our filter method will be an anonymous method, i.e. a method that is not named. This method will be expressed as a lambda expression. We'll now see how we are able to filter a generic list using our filter extension method through calling client code in the main method of our application. Right, so let's go to the .NET Core Console project and write the calling client code in our main method. Firstly, let's reference our two standard library projects from our .NET Core Console project. So let's right-click the Dependencies node in the .NET Core Console project and tick TCP data as well as TCP extensions. So let's test our filter extension method. In a bit, I'll further elucidate why it is important to understand extension methods and lambda expressions with regards to LINQ. Through the magic of how extension methods work in C#, we should be able to call the extension method on any generic list object. So let's define a generic list that is strongly typed as the employee user-defined type. So we have a red squiggly line under our generic list type definition. So to fix this, we need to include a directive at the top of our code to the system.collections.generic namespace. We can see that there is a red squiggly line under the code that strongly types our generic list as the user-defined type employee. So to fix this, let's include a directive at the top of our code to the TCP data namespace. Great! So through the magic of extension methods, we should see the filter method appear in the IntelliSense drop-down list when we add a dot after the employee list variable. Okay, so why are we not seeing the filter method appearing in our IntelliSense drop-down list? The reason for this is because we haven't included a using directive to the appropriate namespace. So let's include a using directive at the top of our code to the appropriate namespace, i.e. TCP extensions. So now if we add a dot immediately after the employee list variable, the magic of extension methods is revealed to us, and we can see our filter method in the IntelliSense drop-down list. So note that when we open brackets to pass in appropriate arguments to the filter method, we see that only one parameter is required. This parameter was the second parameter we defined for this method. So why is the first parameter in the filter method not listed when we open the brackets in this way? Well, the answer to that question is this is how extension methods work. The consumer of the code, i.e. the calling client code, does not need to pass in the first parameter. This is automatically handled behind the scenes, as it were. By default, the first parameter is the object on which the relevant extension method is invoked. So in this case, the list of employees stored in the employee list variable is passed into the filter method into this parameter automatically. So if we look at the filter extension method, we can see that this keyword precedes the definition of the first parameter. The this keyword in this context is telling the C# compiler that the argument passed into this parameter is the object on which the relevant extension method is invoked. So we have access to the argument passed into the first parameter automatically. Okay, so the second parameter accepts a delegate object that points to a method that needs to be created on the calling client. So this method that we'll create essentially tells the filter method how we want our list filtered. So we are able to define this method in the calling client code through the use of a lambda expression. A lambda expression is a concise way to represent an anonymous method. If we look at the definition of the relevant delegate parameter, we need to define a method that accepts an argument of type T and returns a Boolean value. So the C# compiler has enough information to infer that the intended type for type T is employee in this context. We are calling the filter extension method on a strongly typed generic list. The generic list is strongly typed with the employee user-defined type. So say we want to filter our employee list based on the value of each relevant employee item's isManager property. We want to filter the list where we only want to return those employee records where isManager is true. So we want to return all the records from our list where the relevant employees are managers. So to achieve this, we can pass in this lambda expression. Here we are telling the filter method how we want our list filtered. Let's write code to print the results to the console screen. Right, let's run the code. Okay, so we have no data. We of course need to populate our employee list with data. So let's assign the value returned from data.getEmployees to the employees list variable. Right, let's run the code. Great, and you can see that only the employee records where the relevant isManager property value is set to true are returned to the calling client code. Great. And we can of course inject the converse of this logic into our filter method through the relevant lambda expression like this. So we are now saying we only want to bring back employees who are not managers. Let's run the code. Great. And for good measure, let's modify our lambda expression so that the filter method only returns employees that earn less than $50,000 a year. Great. And because we have used generics for our filter method, we can call the filter method on a list of various C# types, including user-defined types. So let's prove this and call our filter extension method on a list of departments. Let's filter the departments based on the department's short name. So let's bring back the finance department and the human resources department. Great. Let's bring back only those departments with IDs greater than 1. So the point of this is to show you the flexibility that the combination of extension methods and lambda expressions create when writing the calling client code. The combination of extension methods and Lambda expressions not only provide this flexibility, but at the same time ensure that the calling client code is clean and concise. Once we understand how extension methods and Lambda expressions work, they are incredibly powerful tools. So, how do extension methods and Lambda expressions work in relation to the topic of this video, LINQ, Language Integrated Query? Extension methods and Lambda expressions are fundamental to how LINQ is implemented in C#. The enumerable class and the queryable class are two static classes that contain extension methods. The enumerable class and the queryable class are both members of the system.link namespace. So to gain access to the extension methods provided through LINQ, we can simply include a using directive to the system.link namespace. Without including a using directive to the system.link namespace, you can see that we are not able to access the where extension method provided by LINQ to perform our filtering operation on a collection that implements the IEnumerable interface. So let's include the system.link namespace. We now have access to LINQ's where extension method, so we can now replace our custom filter extension method with the where LINQ extension method like this. We don't need to create our own filter extension methods to perform such queries on our data. LINQ has got us covered for this. LINQ also provides us with a SQL-like query syntax. So for example, if we wanted to produce a query result by joining selected fields from data selected from our collection of employee objects with selected fields, or field in this case, from data in our collection of department objects, we can use LINQ query syntax to perform our inner join operation on these two collections of data, like this. In the LINQ query, we want to include the department long name field so that we can have a descriptive name for our department in our results set rather than displaying a result that only contains the department ID, which is available in the employee type. So we can achieve this result by using the join clause in a LINQ query to perform our inner join on our collection of employee objects with our collection of department objects. We have the department ID property in the employee type, so we can join using this department ID property in the employee type to the ID property, which is a member of the department type. So say we were to write the equivalent query using Transact SQL against the SQL Server database that contained an employee table with the same data schema as our employee type and a department table that contains the same schema as our department type. The Transact SQL query syntax would look something like this. We are using an inner join to join data in an employee table with data in a department table. We are able to make the join because the employee table contains the department ID, which can be joined in our query the ID of the department table. So you can see the similarities in syntax between the Transact SQL syntax and the LINQ query syntax. The LINQ query is dealing with objects encapsulating the employee and department records. The employee list collection is like the employee table, and the department list is like the department table in this particular context. We have a select clause, a from clause, and a join clause in the syntax for both the LINQ query and the Transact SQL query. However, the from clause in the LINQ query appears at the beginning of the query, and the select clause in the LINQ query appears at the end of the query. So there are differences in the ordering of the clauses when comparing the syntax of the Transact SQL query with the syntax of the relevant LINQ query. An advantage of LINQ is it can be leveraged in our C# code to query data in a standardized way that is independent from the format of the underlying data source. The data source could be a MongoDB database, a SQLite database, a SQL Server database, etc. This will not affect the syntax of our LINQ queries. So the object layer provided by LINQ can be used for abstracting our queries of the data from the underlying data source. And by using LINQ, we also have the added advantage of compile time, strong typing, and the type checking provided by the C# compiler. Let me draw your attention to the select clause. We are able to return the data as an IEnumerable collection of anonymous types. We are assigning the collection returned by the LINQ query to a variable preceded by the var keyword. Beginning with C# version 3, variables that are declared at method scope can have an implicit type var. Through the use of the var keyword, the C# compiler is able to infer the types included in the collection returned from the query. So we are able to return a collection of objects that are of an anonymous type that we have defined directly within the LINQ query. Anonymous types provide a convenient way to encapsulate a set of read-only properties into a single object without having to explicitly define a type first. You can see how the use of anonymous types can provide the developer with flexibility and convenience when constructing relatively complex queries. Note that Microsoft recommends using the query syntax where possible as opposed to using relevant extension methods for the same purpose. This is because of the readability advantage provided in the relevant query syntax. There are, however, times where you'll need to use appropriate extension methods included within the LINQ namespace, because some functionality in LINQ does not have a query syntax counterpart. For example, if we wanted to calculate the average salary for all employees, we would need to use the average extension method like this. The same applies if we wish to query for the highest salary from a list of employee records. We would need to use the max extension method like this. This functionality cannot be performed through the use of query syntax. But where possible, query syntax is preferable due to the code readability advantage that this syntax provides. I hope you've enjoyed this video, which provides an introduction to LINQ. This video was created to help with the understanding of the fundamentals of LINQ, the advantages that LINQ provides, and how we are able to implement basic LINQ queries in code. LINQ provides us with an integration of query capabilities directly into the C# language. It is a very powerful technology that decouples query logic from relevant types of underlying data formats. LINQ provides a layer of abstraction that provides the developer with easy-to-implement syntax for querying collections of objects. The relevant collection types must implement the iQueryable or generic iQueryable interface or the IEnumerable or generic IEnumerable interface. Note that the iQueryable interface inherits from the IEnumerable interface, and the generic iQueryable interface inherits from both the IEnumerable interface and the generic IEnumerable interface. A suite of extension methods and query syntax are made available to C# developers, which provide flexibility when constructing powerful, readable queries against data encapsulated within appropriate C# collections. This video is a basic introduction to leveraging LINQ in the C# language. In the next tutorial, we'll delve deeper into this subject matter. Hi, and welcome to the second part of a video series on LINQ. This video is also the second part of the 7th tutorial in an advanced C# course. LINQ stands for Language Integrated Query. In the first part of this video series, we looked at an overview of LINQ. We discussed that LINQ is the name for a set of technologies based on the integration of query capabilities directly into the C# language. In this video, we'll demonstrate examples where we'll create LINQ queries using method syntax and subsequently show how we can express the same LINQ query using query syntax. As discussed in the previous video, in this series, query syntax is recommended because the logic within the query syntax is easier to read. In this video, we'll look at code examples using the following LINQ operators: select, where, join, and group join. We'll discuss what is meant by method chaining and demonstrate an example that makes use of method chaining in the context of a LINQ query. We'll look at what is meant by deferred execution of LINQ queries and what is meant by immediate execution of LINQ queries. We'll discuss the inherent advantages of deferred execution in the context of LINQ. To further clarify our understanding of deferred execution, we'll create a code example where we'll implement deferred execution for our own custom extension method for an IEnumerable type. We'll demonstrate how the C# yield keyword is implemented in the relevant code example as part of code to implement deferred execution. At the end of the tutorial, we'll look at the join operator and the group join operator. We'll create code examples to help clarify our understanding of these two LINQ operators. In the first part of this video series, we discussed that extension methods and lambda expressions are fundamental to how LINQ works. We created our own extension method for filtering a generic list that can be strongly typed with any C# type, including user-defined types. We then demonstrated how a lambda expression can be created in calling client code, which enables the calling client code to determine how the relevant list of data must be filtered. The reason we created our own filter extension method was to help us understand the fundamentals of LINQ. LINQ functionality is encapsulated in two static classes that are members of the system.link namespace. These two static classes are named queryable and enumerable. These classes mostly contain extension methods As with the previous video in this series, I'm going to demonstrate the code examples in this video on my Mac platform. If you are using a Windows platform, the fact that I'm using Visual Studio for Mac should not be a barrier to follow along with these code examples. The code creation process is almost exactly the same experience when compared to implementing the same code using Visual Studio for Windows. So, let's create a .NET Core console project. Let's name this project LINQ Examples _1. So to save time, let's copy data-related code that we created in the previous video of this series from the appropriate GitHub repository. So please navigate to this URL in your browser to access the relevant GitHub repository. As always, all URLs referred to in these videos can be accessed through appropriate links included below in the description. So let's copy the data-related functionality from this repository to the project we have just created. So in your browser window, click the directory icon labeled TCP data, like this. Click the class icon labeled employee. Let's copy the code for the employee class from this page to our clipboards, like this. and simply paste the contents of the clipboard below the program class in our new project. Let's also copy the code for the department class like this to our clipboards and paste the contents of our clipboards below the employee class within our new project. Let's then copy the code in the data class to our clipboards then paste the contents of our clipboards below the department class in our new project like this. So we have some red squiggly lines within our data class. To fix this, let's include a directive to the system.collections.generic namespace at the top of our code, like this. We are just creating throwaway code in this video to help us understand the relevant topics discussed in this video. So we are not too concerned with code neatness in this video. In our main method, let's create a strongly typed generic list that is strongly typed with the employee user-defined type. Let's name our generic list variable employee list. Let's assign the value returned from the data.getEmployees method to the variable we have just named employee list. This line of code will populate the employee list collection with made-up data that was hard-coded in the data class in the previous video of this series. Let's define a generic list that is strongly typed with our department user-defined type. Let's name our variable for this list department list. Let's assign the value returned from the data.getDepartments method to the variable we have just named department list. This will populate the department list collection with made-up data that was hard-coded in the data class in the previous video of this series. So let's create a LINQ query that makes use of the select LINQ operator. In order to use a LINQ operator, we of course need to include a using directive to the system.link namespace. For this query, we want to select everything from the data stored in our employee list collection. We can do this by simply invoking the select method on the employee list object, like this. The select method is an extension method provided to us through LINQ. We can shape our data through the use of a lambda expression like this. We discussed anonymous types in the previous video of this video series. So, the select operator returns an IEnumerable collection of objects. The lambda expression passed into the select extension method provides an instruction on how we wish to shape each item of data within the returned IEnumerable collection. This is specifically expressed through this anonymous type. Anonymous types provide a convenient way to encapsulate a set of read-only properties into a single object without having to explicitly define a type first. You can see how the use of anonymous types can provide the developer with flexibility and convenience when constructing queries. So here we are providing an instruction that we want each item of data in the returned IEnumerable collection to contain a full name property, which is a concatenation of the first name and the last name properties of the relevant employee record, and a property containing the employee's annual salary. So let's write the code to output the results of this query to the console screen. Let's see the code in action. Great! So if we want to filter this data, we can do this by chaining the where extension method to our select operator like this. Method chaining is a common syntax for invoking multiple method calls in C#. Each method returns an object, allowing calls to be chained together in a single statement without requiring variables to store the intermediate results. So the select operation will return an IEnumerable collection object. We can filter this returned IEnumerable collection within the same link query by chaining the where extension method to the select extension method. The where extension method filters the data stored in the IEnumerable object returned from the select method through a lambda expression passed to the where extension method. The lambda expression provides instructions to the where extension method on how the data must be filtered. Once the data has been filtered through the where extension method, an IEnumerable collection of results is assigned to our results variable. We are then traversing our results using a for each loop and displaying each item in the IEnumerable collection to the console screen. We discussed the var keyword, which allows for local implicit typing within methods in the previous video of this series. Please view the previous video in this series for more details. So here we are implementing link explicitly using the extension methods provided by link. We are using the select operator and the where operator in a link query implemented using method syntax. Let's run the code. Great! We can execute the same functionality using query syntax. So let's comment out the previous code and include a comment to label this code so that we are able to refer to this code later if need be. So let's first implement the link query using query syntax without the where clause. Let's run the code. Great! Let's implement the link query implemented using query syntax, and this time include the where clause within the link query using query syntax. Let's run the code. Excellent. And we get exactly the same result when compared to running the query that we implemented using method syntax. But we have constructed our link code using link query syntax as opposed to using relevant extension methods. The query syntax is more readable, and we don't need to chain our extension methods, as we did in the previous example where we changed the where extension method to the select extension method. Let's take a closer look at our query where we used method syntax versus the same query where we used query syntax. Note that standard query operators in our query syntax are converted into extension methods at compile time. So standard query operators are essentially the same as their counterpart extension methods. Microsoft recommends using query syntax as opposed to directly implementing the relevant extension methods where possible. As discussed, this is due to the readability advantage inherent in the query syntax. There are times when you will need to use extension methods directly where equivalent query syntax is not available. We looked at a few examples of this in the previous video of this series. For example, using aggregate functionality, like for example finding the average, min, or max annual salary for a collection of employee records. We would need to use the respective average, min, or max extension methods to calculate and return the relevant values. The developer is able to execute link queries with deferred execution or immediate execution. So let's first understand what is meant by deferred execution. Deferred execution means that the evaluation of an expression is delayed until its value is required. This improves performance because only necessary executions are carried out, i.e. at the point where the relevant value is required. Let's use our last query example to illustrate this point. So when we first assign the value returned by our query to our results variable, the query is not executed. It is only when we traverse the items in our results variable that the actual execution takes place, i.e., with each iteration of the for each loop, an execution is performed, whereby the relevant item is evaluated and returned from the collection. Another advantage of deferred execution is that an update to the relevant data collection will immediately be reflected in the results. So, for example, let's add a record to our employee collection. Note, the salary for this new employee is above 50,000, so this employee should appear within our results. Let's run the code. And you can see that this is proof that the results are evaluated within the for each loop, and the query itself is not executed at the line of code where the relevant query is located. The execution of the query is deferred until the results are traversed within the relevant for each loop. To further understand the concept of deferred execution, let's create a code example where we'll implement deferred execution for our own custom extension method for an IEnumerable type that is strongly typed as the employee user-defined type. Let's create a static class named enumerable collection extension methods. Let's create a static method within the static class that we have just created, and let's name this method getHighSalariedEmployees. We discussed extension methods in the previous video for this video series. For more information on extension methods, please access a link to this video. As discussed, a link to this video is available below in the description. So let's implement the code for the getHighSalariedEmployees extension method, like this. Note the use of the yield keyword. You can use a yield return statement to return each element one at a time. The sequence returned from an iterator method can be consumed by using a for each statement or LINQ query. Each iteration of the for each loop calls the iterator method. When a yield return statement is reached in the iterator method, the relevant value in the IEnumerable collection is returned, and the current location in code is retained. Execution is restarted from that location the next time that the iterator function is called. Let's go to our main method and implement a query that calls our extension method on the employee list collection. Let's copy and paste the code that we have already written to traverse the results and output the relevant data. And let's add another employee record to the employee list collection as we did before. Let's run the code. And you can see that the new employee record is reflected in the results. The results are kept up to date due to deferred execution. Note that deferred execution reevaluates on each execution, which is known as lazy evaluation. The converse of deferred execution is immediate execution. Immediate execution means the relevant query is executed immediately. To execute a query immediately, we need to apply an appropriate toConversion method to the query. So let's copy the previous code example. Let's uncomment the relevant code. Let's change this code so that the query executes immediately. We can use the toListConversion method for this purpose. We are using query syntax here, so in order for us to use the toListConversion method, we first need to wrap the relevant query in brackets, add a dot, and then the toListConversion method. We are explicitly typecasting the IEnumerable value returned from the query to the list type through the implementation of the toListConversion method. We are also executing the query immediately. Let's uncomment the rest of the relevant code for this example. And let's run the code. You can see that the execution of our query is immediate, because this time, after we've added a new employee, the query has not been evaluated again to include the new employee record in the results. This is, of course, why the new employee does not appear within the results output to the screen. This proves that our query has executed immediately at the line of code where the query is located. And remember that query syntax does not support toOperators, so we need to wrap our query in brackets, as we have done here, and call whichever toMethod is appropriate, for example, toList, toArray, or toDictionary. By calling the relevant toMethod, in this case the toList method, we are causing our query to execute immediately. Without the toConversion method, the relevant query execution would be deferred until the relevant results are iterated. So let's move on to the join operator, and then we'll look at the group join operator and highlight the difference between these two join operations. In the previous video in this series, we looked at the join operator and discussed how we can perform an inner join on two IEnumerable collections using a LINQ query. So here we have two collections that we wish to join. In this specific use case, we need to include a descriptive department name in our results displayed to the user. We only have a department ID field in our employee type, so in order to merge the properties from our employee type with the relevant property from our department type, we need to join records of type department that reside within our department list collection with records of type employee that reside within our employee list collection. We can do this by matching the ID field in the department records that reside in the department list collection with the department ID property of employee records that reside in the employee list collection. We can do this through LINQ by using the join operator. Later, we'll demonstrate a join operation, but using the group join operator. We'll also discuss the differences between the join operator and the group join operator. Let's look at the relationship between the collection of department records with the collection of employee records. Department records have a one-to-many relationship with employee records. A specific department can have many employees as members. A specific employee cannot belong to more than one department at a point in time. Data collections can also have one-to-one relationships with one another, or many-to-many relationships with one another. So in this example, we are going to look at how we can use LINQ to implement a join operation between two collections of records that have a one-to-many relationship with one another, i.e., one department to many employees. So let's implement a query that joins the department list collection with the employee list collection, where the ID property of the relevant objects of type department match the department ID property of the relevant objects of type employee. So the syntax for this LINQ query would look like this, when we implement the join operation using method syntax. So to join department records to appropriate employee records, we can use the join extension method and invoke the extension method on the department list collection. The first argument we need to pass into the join method is the collection on which we want to join the department list collection. So we pass in the employee collection object here. The second argument is the key from the outer collection, the department list collection. So the outer join key is the ID property that resides in the department type. We can express this argument as a lambda expression like this. The third argument is the inner join key, which is the department ID property, which is a member of the employee type. We can express this argument as a lambda expression like this. So we are joining on the ID property, which is a member of the department type, with the department ID property, which is a member of the employee type. We can define an anonymous type where we are able to shape the data for each item in an IEnumerable collection that we want returned from the relevant query. Here we are defining an anonymous type within our link query that includes the employee full name, which is a concatenation of the employee's first name and last name, the employee's annual salary, as well as the relevant department object's long name property. The long name property will give us a descriptive department name in our results. We are including the department type's long name property in the relevant anonymous type. This is the whole point of joining the department list collection with the employee collection, so that we are able to include a descriptive department name within our results. We only have the department ID as a member of our employee type, so if we only returned results from the employee list and wanted to include department information, we would be restricted to the department ID property, which is an integer value and is unlikely to be meaningful to a user. Let's run the code. Great! But as discussed, where it is possible to use query syntax rather than method syntax for our link queries, we should use query syntax because the logic expressed in the relevant query is far easier to read. So let's write the same query using query syntax. As you can see, it is far easier to read, and it is also similar to query languages with which we may already be familiar, for example, Transact SQL. Let's express what a similar query in Transact SQL might look like. So let's imagine that we have a table in a SQL Server database that could map to our employee type. Let's say this table has the same name as our employee type. Let's also imagine that we have a table in the same SQL Server database that contains a table schema that could map to our department type. Let's say this table has the same name as our department type. So the Transact SQL would look something like this. You can see how the from clause, the join clause, and the select clause are implemented in both the link query syntax and the Transact SQL syntax. Even though the link query contains the same clauses in a different order to the comparative clauses in the Transact SQL query, for someone who is familiar with Transact SQL and not necessarily familiar with link query syntax, this link query syntax at a glance should be fairly easy to understand. So the point here is that link query syntax is similar to query syntax with which many of us will already be familiar. So this makes the implementation of link queries using query syntax more intuitive. As discussed, the link query syntax is also more readable than the equivalent link query implemented using method syntax. So the key takeaway here is to use link query syntax rather than method syntax where possible, because it is more intuitive to implement and easier to read. Let's run the code. Great. So let's look at the group join link operator and why we might want to use the group join operator in our link queries. We have just performed an inner join using the join operator. This query will only return those records based on the ID property of relevant objects of the department type in the department list collection, matching with the department ID property of relevant objects of the employee type in the employee list collection. Diagrammatically, an inner join query can be represented like this. What if we wanted to return, through a link query, all the department records in our department list collection and only employee records where the department ID property of employee objects in the employee list collection match the ID property of department records in the department list collection? So if we were to write the Transact SQL version of this query, it would look something like this. We would use a left outer join to achieve the desired result. This query would bring back all department records, but only those employee records where the relevant employee records department ID values match the ID property of the relevant department records. So, diagrammatically, we can represent a left outer join query like this. So let's look at the diagram representing an inner join operation and compare the diagram to the diagram representing the left outer join operation. So let's use our group join operator in a link query to return all department records from the department list collection, but only the employee records from the employee list collection with a department ID property that matches an ID property of a department record in the department list collection. So here we are implementing our query using method syntax. You can see the implementation of the group join operation using method syntax is very similar to the way we implemented the join operation in the previous example. Let's run the code. Note, the way we have structured our output is clearly different when outputting the results of our group join query when compared to the way we structured our output of the results of our join query. But note that at the moment the same join between department records and employee records has occurred. The reason for this is not because the group join and the join operators perform the same type of join operation. It is because currently each of the records in the employee list collection match with a department record in our department list collection. Let's change our data to highlight a key difference in the join operation and the group join operation. Let's do this by going to the code where we have hard-coded, made-up employee and department records and added these records to their respective collections. Let's ensure that the technology department, which has an ID of 3, does not match with a department ID property of any of the employee objects in our employee list collection. We only currently have one employee that is in the technology department according to our data. Let's change the relevant department ID so that there are no employees that are members of the technology department. So let's change this department ID property. Now, no employees are members of the technology department according to our data. Let's run the code. So you can see our technology department record is being returned along with all the other department records in the department list collection, even though its ID property doesn't match the department ID property of any employee records stored in the employee list collection. So simply put, department information for departments that contain employees are included in the query results, and departments that don't contain any employees are also included in the query results. In this example, the technology department is returned even though it contains no matching employee records. So here we have performed a left outer join query using link's group join operator. So let's rewrite this link query using query syntax. You can see here that the group join extension method does not get explicitly called when we implement our query using query syntax. The into keyword is used within the query to create a group of employees for each department. So as discussed, link query syntax does not match exactly when comparing link query syntax to familiar query languages like Transact SQL. But in many ways, it does resemble a language like Transact SQL. In this sense, link query syntax is more intuitive to implement than method syntax when implementing link queries. And just to labor the point, as discussed, it is also better to implement link query syntax for our link queries than implementing method syntax for the same purpose because of better readability. Let's run the code. Great! And we get the exact same result as when we ran the same query that was implemented using method syntax. Now that we have changed the data so that the technology department does not match with any employee records, let's run our join operation that we created earlier. Notice that the results of the join operation doesn't include the technology department. This is because the join operation performs an inner join, and with the group join operation, we are able to perform a left outer join operation. So let's comment out our join query and uncomment our group join query. And for good measure, let's run the code again. And as you can see, the technology department is now included in the results displayed to the screen, even though the technology department does not have any matching employee records. Great! So the left outer join operation returns all records from the outer left collection in the query, but does not return records from the inner collection, where the inner collection records do not match any of the outer collection records. So if there were employee records in the employee list collection that did not match any of the department records in the department list collection, these employees would not appear in the results outputted to the screen. We can prove this. Let's change the department ID of this employee record where the first name property is Bob and the last name property is Jones. We have changed the department ID property for this record to 6, and there is no matching department record, i.e. no department record has an ID of 6. Let's run the code. And you can see that the employee record with first name Bob and last name Jones does not appear within the results. However, even though the Human Resources Department has no matching employee records, it is still included in the results outputted to the screen. Great! Let's add Bob Jones back into the Human Resources Department like this. And let's run the code. Excellent! So hopefully this made it clear how we are able, through LINQ, to use the join operator to perform inner join queries between two object collections, and how we are also able to perform left outer join queries using the group join operator. Hi, and welcome to the third part of a video series on the LINQ technology using C#. This video is also part of the 7th tutorial in an advanced C# course. LINQ was introduced with C# version 3, which was released on the 19th of November 2007. LINQ stands for Language Integrated Query. In this video, we are going to focus on code examples that make use of several LINQ operators. The code examples demonstrated in this video will hopefully help us gain an understanding of a broad array of operators that are made available to us through LINQ. We'll learn how we can use these operators to query and transform data. This quote from the Microsoft Docs provides a basic definition of standard query operators and can be found at this URL. The standard query operators are the methods that form the LINQ pattern. Most of these methods operate on sequences, where a sequence is an object whose type implements the generic IEnumerable interface or the generic IQueryable interface. A lot of the more frequently used query operators have dedicated C# keyword syntax that enables them to be called as part of a query expression. As discussed in the previous video in this video series, it is advantageous to use query syntax rather than method syntax where possible because query syntax is more readable. Note that query expression clauses are translated into calls to query methods at compile time. For a useful tabular representation of standard query operators that have equivalent query expression clauses, please navigate to this URL. We discussed what is meant by deferred execution and immediate execution in the previous part of this video series. For a useful tabular classification of operators in terms of deferred execution or immediate execution, please navigate to this URL. For additional information on deferred execution versus immediate execution and method syntax versus query syntax, please view the second part of this video series. So to gain an understanding of several useful LINQ operators, let's create a few code examples. As with the previous video in this series, I'll be demonstrating these code examples on my Mac platform using Visual Studio for Mac. The code creation process for these code examples is almost exactly the same process as creating the equivalent code examples on a Windows platform using Visual Studio for Windows. The fact that I'm using Visual Studio for Mac should not be a barrier for a learner to follow along with the creation of these code examples. So, let's start by creating a .NET Core Console project. We created a project in the previous video named LINQExamples_1. Let's name this project LINQExamples_2. In order to save time, let's copy data-related classes that have already been created in the previous videos of this series and incorporate these classes into our new project. These classes contain class definitions for an employee and a department record, as well as code that adds several made-up objects of type employee and department to their respective collections. As in the previous parts of this video series, we can then use these collections of strongly typed objects in our LINQ query examples. So to copy the relevant code, let's navigate to this URL, i.e. to a GitHub repository that was created in the previous video. Let's click on the directory icon labeled LINQExamples_1. Then let's click on the file icon labeled program.cs. Let's copy the employee class to our clipboards. And paste the contents of our clipboards within the new project that we have just created. Let's copy the department class to our clipboards and paste the contents of our clipboards below the employee class within our new project. Lastly, let's copy the data class to our clipboards and paste the contents of our clipboards below the department class within our project. So in the previous video, we looked at the following operators: the select projection operator, the where filter operator, the join and group join operators. In this video, we'll create code examples that implement the following operators. We'll start by looking at the following sorting operators: order by descending, then by, and then by descending. We'll then look at these grouping operators, group by and toLOOKUP. We'll then look at these quantifier operators, all, any, and contains. We'll then look at the following filtering operator, of type. Note that another example of a filtering operator is the where operator. We have looked at the where filter operator in the previous parts of this video series. Lastly, we'll look at the following element operators: element at or default, first or default, last or default, single, and single or default. We'll look at even more link operators and create code examples in the next video. The next video will be the final video in this video series on link. Right, let's get started. So let's start by looking at the data-related classes that we copied from GitHub. We have the employee class, which provides a definition for an employee record. We have the department class, which provides a definition for a department record. We have the data class that contains code where lists of hard-coded, made-up employee and department objects are added to their respective collections within their respective methods and returned from their respective methods. In the previous video in this series, we looked at join operators, namely the join operator and the group join operator. So in the context of join operations, the department collection has a one-to-many relationship with the employee records in the employee collection. This simply means that one or many employees can be members of a specific department. A specific employee can be a member of only one department at a point in time. So let's go to our main method. We can use the data.getEmployees method to return a collection of made-up employee records. Let's use this method to assign the relevant collection of employee records to a local variable named employee list. The employee list variable is defined as a generic list that is strongly typed as employee. So here we have red squiggly lines because we need to include a using directive to the system.collections.generic namespace. Let's use the data.getDepartments method to return a collection of made-up department records that have a one-to-many relationship with the relevant collection of employee records, and let's assign the relevant returned collection of department records to a variable named department list. The department list variable is defined as a generic list that is strongly typed as department. So let's get into the creation of our examples. Sorting operators. Order by. So let's create an example for the order by operator. In this example, we want to return all employee records from the employee list collection and order by department ID. To make things a little bit more interesting, let's say we want to include the department name within our outputted results. The problem here is that the department name does not exist in the employee type, so we need to join the employee list collection to the department list collection so that we can include the department name in our results. We can do this by using the join operator. So let's write this query using method syntax so that we can see all the link extension methods used in the relevant query. So we first need to make sure that we include a using directive to the system.link namespace. This directive will give us access to the relevant link operators that we will be implementing in our code examples. We know that the system.link namespace contains two static classes, namely enumerable and queryable, and these static classes mostly contain extension methods. Our link operators, which are implemented in the form of extension methods, are implemented within the enumerable and queryable static classes. So this link query joins the employee list collection to the department list collection on the department ID property of each of the relevant employee records with the ID property of relevant department records. Before we run this query, let's alter the data a bit. Let's make the employee record pertaining to Sarah Jameson a member of the technology department by changing the relevant department ID property from 2 to 3. Let's also change the department for the employee record pertaining to Jane Stevens to the technology department by changing the relevant department ID from 2 to 3. This change to the data will make the effects of our sorting operators more apparent when we view our results. So if we run the query first without the use of any order by operators, note that the data appears to us in the same order as it was added to the employee list. But now let's say there is a requirement to order our results by the department ID property in ascending order. We can do this by chaining the order by extension method to the end of the query, like this. For more information on method chaining, please view the previous video in this series. So we can pass in a lambda expression to the order by extension method to indicate that we wish to order the results by the department ID property. Let's run the code. And you can see that the results are now ordered in ascending order by department ID. If we look at the code that added each department to the department collection, we can see that the Human Resources Department has an ID of 1, the Finance Department has an ID of 2, and the Technology Department has an ID of 3. Our results have been ordered in ascending order based on the department ID property of the employee record. So we can clearly see the effects of the order by operator on our results. Great! If the requirement changed such that we needed to order our results by the department ID property in descending order, we can chain the order by descending extension method instead of the order by extension method for this purpose. Our results are now ordered by department ID in the reverse order when compared to the previous output. Great! So let's say that we want to order our results by the department ID property in ascending order and then by the annual salary property also in ascending order. So let's replace the order by descending extension method with the order by extension method in our results like this. Then let's chain the then by extension method to the query like this. We can then pass a lambda expression to indicate that we wish to further order our results by the annual salary property. The then by extension method will order the results produced by the order by sorting operator in ascending order. Great! And if we want to order by the annual salary property in descending order, we can replace the then by extension method with the then by descending extension method for this purpose. Excellent. We can represent sorting operations within linked queries that are represented using query syntax like this. Note the order by and descending keywords in the query syntax version of the relevant query. We use the order by keyword within our query to order by our first specified property. If we want to subsequently sort on other properties instead of chaining the then by extension method to our query in query syntax, subsequent properties by which we wish to sort are separated by commas. The descending keyword can follow any of the properties that we wish to sort in descending order. The default order is ascending order. So let's look at the group by and to-lookup grouping operators. Let's start with the group by operator. So this operator is akin to the group by clause we would apply in a Transact SQL query. So we can implement the group by operator using the group by extension method, or the group and the by keywords within query syntax to perform the same operation. So let's say we wish to query the employee list collection and group our results by the department ID property. The query using query syntax would look like this. This query is simply grouping our results by the department ID property. Using method syntax, this query would look like this. In all of the LINQ query examples using query syntax that we have looked at up till this point, in this video series, we have ended all our queries with a select operator. Notice that this query does not end with a select operator. It is important to note that a LINQ query implemented in query syntax must either end with a select operator or a grouping operator. Notice how this query does not end with a select operator, but a grouping operation is being performed at the end of this query. So we can traverse the results of this grouping operation using nested for each loops. The outer loop traverses each group that has been created based on the department ID property. The inner loop traverses the item members within each of the groups that have been created in our query based on the department ID property. Great! We could also include the order by operator within our query like this. Let's run the code. Great! We can implement the same query using method syntax using the to-lookup extension method like this. Great! We can also include sorting functionality through the order by operator through the implementation of method chaining like this. Great! Note that the to-lookup method performs the same operation as the group by operator. The only difference is the execution of the group by operation is deferred, whereas the execution of the to-lookup operation is executed immediately. We discussed deferred execution and immediate execution in the previous part of this video series. For more information on deferred execution and immediate execution, please view the second part of this video series. A link to this video has been included below in the description. Note that the results returned from a group by operation and a to-lookup operation return a group contained in a special type of collection that implements an iGrouping generic interface . So let's look at the all, any, and contains quantifier operators. Let's first look at the all and any operators. Let's create a variable named annual salary compare and assign it with a value of 20,000. Let's implement a block of code related to the all operator. Let's implement a similar block of code related to the any operator. So, the all and any operators return a Boolean value. The return value will equal true if the elements in the relevant collection satisfy a condition passed to the relevant method. This condition can be passed in the form of a lambda expression. This query will return true if all employee records have annual salary property values that are greater than 20,000. This query will return true if one or more employee records have an annual salary property value that is greater than 20,000. Let's run the code. Great, this is an expected result. Let's change the annual salary compare variable to 100,000. Great. And let's change the annual salary compare variable to 40,000. So let's move on to the contains operator. So we want to be able to assess whether an employee record exists within our collection of employee records. The contains operator will return true if we pass in an object that is equal in value to an object within the relevant collection. To understand how the contains operator works, let's create an employee record that we know matches an employee record within the employee list collection. Let's copy this record for the employee named Douglas Roberts that is a member of the relevant employee collection. And paste it in our main method. Let's name the variable that stores a reference to the employee record we wish to find within the employee list collection search employee. So how can we assess whether the employee record pertaining to Douglas Roberts exists within the employee list collection? We can use the contains extension method. We can simply pass the variable we named search employee to the contains extension method, which we have invoked on our employee list collection object. So the contains method returns true if the search employee object matches any of the objects within the employee list collection, and false if the search employee object does not match with any of the objects stored within the employee list collection. So let's write code to write an appropriate narrative to the screen based on the Boolean value returned by our query. Let's run the code. And this is not the result we expected because we literally copied and pasted the code representing one of the employee objects that has been added to the employee list collection from our data class to the main method as our search object. So Y is our output indicating that the search employee object does not match any of the objects stored within our employee list collection. This result is unexpected. The answer is that the compiler knows how to compare built-in C# types like, for example, integer or bool. The employee type is a user-defined type or custom type. We need to tell the compiler how we wish to compare two objects of type employee to establish whether two employee objects are equal. So we can do this by creating a class that implements the generic iEquality comparer interface. The iEqualityComparer interface is a member of the system.collections.generic namespace. We have already included a using directive to this namespace within our code. So let's create a class named EmployeeComparer, and let's indicate that we want the EmployeeComparer class to implement the iEqualityComparer generic class that is strongly typed with the employee user-defined type. So let's hover our mouse pointers over the red squiggly line and create the stubs for the methods that we need to implement, like this. So two method stubs have been generated, one named equals and the other named getHashCode. So the getHashCode method is used for the purpose of uniquely identifying an object. We can implement the code for the getHashCode method by returning the hash code of the ID property of the relevant employee object, like this. The equals method must be implemented in a way that establishes how we wish employee objects to be compared when determining whether two employee objects are of equal value. So let's say that we are satisfied with comparing the relevant employee objects based on their ID, first name, and last name properties to establish equality between the relevant employee objects. So we can achieve this with the following code. If the relevant properties are equal, return true, else return false. So we are already passing in the search employee object to the contains method. Let's also pass a newly instantiated object of type EmployeeComparer to an overload version of the contains method, like this. And now we are telling the compiler how we want to compare our employee search object with the objects stored within the employee list collection. Let's run the code. And this is an expected result. The contains method now returns true as expected because our search record matches the employee record for Douglas Roberts within the collection on which we are performing our search. Great. So now let's look at the of-type filter operator. So before we use the of-type filter operator in our code examples, let's create a method named getHeterogeneousDataCollection. Heterogeneous in this context, of course, is referring to the storage of objects of multiple different data types within the same collection. So we can store objects of multiple different data types in an array list. Note that Microsoft does not recommend using array lists for new development. It is far better to use strongly typed lists to store collections of data. For more detail as to why strongly typed lists are recommended, please view a video on generics created by this channel. A link to this video has been included below in the description. So, a use case where we could apply a link query on an array list could be perhaps we have a legacy piece of code that includes an array list containing objects of multiple types, and we need to filter the relevant array list based on specific types. We can achieve this using the of-type link operator. We'll look at how we can do this in a bit. Let's first add some made-up data to an array list. So the array list stores integers, strings, objects of the employee user-defined type, and objects of the department user-defined type. Let's go to our main method and write code to use the of-type operator to query this array list based on specified data types. Let's query for all string values in our array list. Great. So let's query all integer values in our array list. Great. Let's query for all objects of the employee user-defined type. Great. Let's query for all objects of the department user-defined type. Excellent. So you can see how we can query an array list for objects of a specified type using generics and the of-type operator by passing in the relevant type between angle brackets like this. This will return those objects within the array list that are of the specified type. Let's move on to the element operators. Let's look at the element at or default, first or default, last or default, single, and single or default element operators. So let's first look at the element at operator. So the element at operator is used for querying for an item in a collection that resides at a specified ordinal location within the relevant collection. So we can pass an integer value representing the relevant element's location in the relevant collection into the element at method to return the desired item's value from the relevant collection, like this. Great, and our query has returned the value for the relevant element. But what happens if we pass in a value representing a position in the relevant collection where an element does not exist? So let's try this. Let's pass in a value of 8. Right, so it is important to note that no item exists within the relevant collection at ordinal position 8. So in this case, an argument out of range exception is thrown. This brings us to an important point about the difference between the element at and the element at or default method. If we replace the element at method with the element at or default method, and we query the relevant collection for an item at a position where the desired item does not exist within the relevant collection, the element at or default method does not throw an exception, but rather returns the default value for the desired item's relevant data type. Let's briefly discuss what we mean by a default value for a particular data type. The C# language associates default values for C# data types. So if, for example, we are querying a collection of integers using the element at or default method for a value that did not exist at the specified location in the relevant collection, the element at or default method would return the default value for the integer data type, which is a value of 0. The integer value of 0 is the default value for the integer data type in C#. If, however, we are querying a collection containing a reference type object like an object of our user-defined type employee, the default value returned by the element at or default method would be null. Null is the default value for reference type data types like user-defined types or the string data type. For more detail regarding default values in C#, please navigate to this URL. So let's use the element at or default method to query the relevant collection of employees for a value at position 8, i.e. where no employee object is present within the relevant collection. We can then write code to check if the returned value is null. And you can see that an exception is not thrown and no results are outputted to the screen, which is an expected result because the query returned a null value. Let's pass in a value of 2 and then 1. And in both cases, the appropriate result is outputted to the screen. So let's write code to output an appropriate narrative to the user based on the value returned from the element at or default method. So let's pass in a value of 12. The output indicating that the return value is null, i.e., the employee object does not exist in the collection, is outputted to the screen. This is an expected result. Great. So the first operator returns the first element in a collection if no condition is specified. We have the option of passing a condition to the first method, or we can leave the brackets following the first method empty. If we do not specify a condition, the query will return the first element in the relevant collection. If a condition is specified, the first operator will return the first element in the collection that satisfies the specified condition. We can specify a condition in the form of a lambda expression. Right, to prove this, let's first create a strongly typed list of integer values. So if we query this collection using the first operator and don't provide a condition passed as an argument to the first method, the query returns the first item in the collection as expected. So let's pass a condition in the form of a lambda expression to the first extension method. So this condition is simply querying the collection for the first even number in the collection. Let's run the code. Great. But now what happens if we alter the collection of values so that no value satisfies the condition, i.e. no even numbers exist within the relevant collection? An invalid operation exception is thrown. So if we don't want an exception to be thrown, we can replace the first operator with the first or default operator. As you may have guessed, where no items in the relevant collection satisfy the relevant condition, this method will not throw an exception, but will rather return the default value of the relevant data type. We know that the default value for the integer data type is 0. Let's write code to output an appropriate narrative to the screen if the relevant condition is not satisfied. Let's run the code. And this is an expected result. So let's include an element in the relevant list that does satisfy the condition. Excellent. So the last and last or default operators work in much the same way as the first and the first or default operators. The only difference is that the last item in the collection is returned where no condition is specified. The last item that satisfies a specified condition in the collection is returned when a condition is specified. The last method will throw an exception if an appropriate element is not present within the relevant list. We can use the last or default method rather than the last method to return the default value for the relevant data type in the case where an appropriate element in the relevant collection is not present. Great! So let's move on to the single and single or default element operators. The single operator returns the only element in a collection or one element that satisfies a specified condition from a collection. We have the option of passing a condition into the single method through the use of a method overload, or we can leave the brackets following the single method empty, which means we have chosen not to pass in a condition into the single method. If we choose not to pass in a condition into the single method, and there is more than one element or 0 elements in the collection, an invalid operation exception will be thrown. If, however, there is only a single element in the collection, the value for this element will be returned by the query. If we do choose to pass in a condition and 0 or more than one element satisfies the condition, an invalid operation exception will be thrown. If we pass in a condition to the single method and only a single element satisfies the condition, the value for this single element will be returned from the relevant single operation. Let's apply the single operator to a collection of employees. Let's first modify the data for our list of employees so that only one employee element exists within the relevant employee collection. Let's write code using the single operator to query the relevant employee list. Great, this is an expected result. Let's now include the employees that we just commented out back within the relevant employee list. Let's run the code. And an invalid operation exception is thrown as expected. This is because more than one employee resides in the list. If there is only one item in the relevant collection, the value for this item is returned. If there are 0 items or more than one item in the collection, and a condition is not specified for the single operator, an invalid operation exception is thrown. So let's test the single method, and this time specify a condition where one item within the relevant collection satisfies the specified condition. Great! Let's specify a condition where more than one item in the relevant collection satisfies the specified condition. As you can see, an invalid operation exception is thrown. So let's test the same scenario, i.e., more than one element in the relevant collection satisfies the specified condition, but this time let's use the single or default method. That's interesting. So note, where more than one element satisfies the specified condition when the single or default method is applied in the relevant query, an invalid operation exception is thrown, just like when the single method is applied to perform the same operation. So we can use the single or default method instead of the single method if we don't want an exception to be thrown under the scenario where no elements exist within the collection. The default value for the data type will instead be returned by the query. If a condition is specified for the single or default method, and no elements satisfy the condition, the same result will be produced, i.e., the default value for the data type of the element stored in the collection will be returned by the query. If a single item is present within the relevant collection, and the single or default method is applied to perform a query against the relevant collection, the single element's value that exists within the relevant collection will be returned by the query. Hi, and welcome to the fourth and final part in this video series on the link technology using C#. This video is also part of the 7th tutorial in an advanced C# course. This video is a continuation of the previous 3 videos in this video series on LINQ, so I recommend viewing the previous 3 videos in this video series before viewing this video. In the previous video in this series, we looked at code examples where certain LINQ operators were implemented to query and transform data. This video is a continuation of the previous video in this series, where we'll create code examples using some of the other LINQ operators to gain a broader understanding of what can be accomplished using the LINQ technology in C#. So in the previous videos in this series, we have created code examples using the following LINQ operators. The sorting operators, order by descending, then by, and then by descending. The grouping operators, group by and to lookup. The quantifier operators, all, any, and contains. The filter operators, of type and where. The element operators, element at or default, first or default, last or default, single, and single or default. The join operators, join and group join. We have already looked at the select projection operator, and we'll also look at the select operator in this video, and in addition to this, we'll also look at the select many projection operator. So in this video, we'll look at the following LINQ operators. The equality operator, sequence equal. The concatenation operator, concat. The set operators, distinct, except, intersect, and union. The generation operators, default if empty, empty, range, and repeat operators. The aggregate operators, aggregate, average, count, sum, and max. The partitioning operators, skip while, take, and take while. The conversion operators, toList, toDictionary, and toArray. And lastly, the projection operators, select and select many. We'll also look at the following keywords that are useful when used in queries implemented in query syntax, namely the let and into keywords. We have looked at the select projection operator already in previous videos, but we'll look at this operator again in this video, as well as look at the select many projection operator. We'll then be able to gain an understanding of the difference between the select and the select many projection operators. As in the previous videos, I'll be demonstrating the code examples on my Mac platform. If you are using a Windows platform to follow along, the experience of creating these code examples will be almost exactly the same. So the fact that I'm using Visual Studio for Mac should not be a barrier for a learner using Visual Studio for Windows to follow along with the creation of these code examples. Okay, so let's create a .NET Core console project. So the official release of .NET 5 has now been released. So I'll be running this project using the new .NET 5 .NET Runtime. For more information on the significance of the .NET 5 runtime, please view the second part of this advanced C# course. I've included a link to this video below in the description. The project we created in the last video was named LINQExamples_2. Let's name this project LINQExamples_3. So as we did in the previous video, let's navigate to this URL where we can access code on GitHub for the project that was created in the previous video of this series. Here we can copy the data-related code that we created in our previous project so that we can reuse these data-related classes in this project. Let's click the directory icon labeled link examples _2. Let's then click the file icon labeled program.cs. Let's copy the class named employee and paste the contents of our clipboards to our new project. Let's do the same for the department class. And the data class. Okay, so we won't be using the getHeterogeneousDataCollection method that resides in the data class in this video, so let's delete this method. Let's refresh our memories about the classes we have just copied and pasted from GitHub. The employee class contains a definition for an employee record. The department class contains a definition for a department record. The data class contains hard-coded, made-up data for employee records and department records. The employee records are stored in a generic list strongly typed as employee. The department records are stored in a generic list that is strongly typed as department. We can access the data stored in the employee list collection from calling client code, in this case, this will be the main method, by calling the static method named getEmployees. We can access the data stored in the department list collection by calling the static method named getDepartments. Note that the data class in which these methods reside is a static class. Let's navigate to the main method, and before we create our example code, let's add the appropriate using directives. First, let's add a using directive to the system.collections.generic namespace. The generic list type is a member of this namespace. Let's also add a using directive to the system.link namespace. Once we have added our system.link using directive, we can access our link operators on collection types that implement the IEnumerable interface. So, for example, list types implement the IEnumerable generic interface. So we are able to access extension methods stored within the enumerable static class, which is a member of the system.link namespace, by including a using directive to the system.link namespace. The queryable static class also includes link extension methods and is a member of the system.link namespace. For more information on how extension methods work in C#, please view the first video in this video series. A link to this video has been included below in the description. Before we get started creating our code examples, I want to draw your attention to what might be an issue for Visual Studio for Mac users. When we run our code interactively through Visual Studio for Mac, by default, the output may appear in the terminal console window within Visual Studio for Mac, like this. This is absolutely fine for testing code, but you may prefer to present the output externally, i.e. in a terminal console window outside of Visual Studio for Mac. If you would prefer to present your output externally, i.e. outside of Visual Studio for Mac, please navigate to Visual Studio for Mac Preferences, then under the heading marked Other, select the item labeled Terminal. In the right pane of the relevant dialog box, ensure that the Enable Integrated Terminal checkbox is unchecked. This is obviously not a functional issue, it really comes down to personal preference. Let's define a generic list variable named employee list that is strongly typed as employee, and let's assign the collection of employee records returned by the data.getEmployees static method to the employee list variable. Let's define a generic list variable named department list that is strongly typed as department, and let's assign the collection of department records returned by the data.getDepartment static method to the department list variable. Okay, so we are now ready to query and transform data using LINQ. So let's start with the equality operator, sequence equal. So the use case here is we want to compare two lists of data, and we want to know if these two lists contain elements of equal value and each element in each of the relevant lists are stored in the same order. If each item in each list matches in terms of value and order, the sequence equal method will return true. If any of the items in each of the relevant lists does not match in terms of value and order, the sequence equal method returns false. Let's create a generic list named integer list1 that is strongly typed as integer. Let's copy and paste this line of code to the next line. Let's change the name of the second list to integer list 2. Let's run the code. And the sequence equal method returns true, because the values and sequence of elements in integer list 1 is identical to the values and sequence of elements in integer list 2. Let's change the order of the items in integer list 2, so this sequence of values is not equal to the sequence of values stored in the list named integer list 1. Let's run the code, and this is an expected result. Let's change integer list 2 once again for good measure. And this is an expected result. Great. So let's change the data in integer list 2 so that the order and values in the lists are equal. And now the result is true, which is an expected result. That was pretty straightforward, i.e., comparing two sequences of values of a primitive data type, i.e. the integer data type. But what if we want to test this type of equality between two lists that are strongly typed with a complex type? Like, for example, our employee user-defined type. So let's define a variable named employee list compare as a generic list type that is strongly typed as employee, and let's assign the collection returned from the data.getEmployees static method to our employee list compare variable. Let's run a sequence equal operation and compare the values stored within our employee list compare collection with the values stored within the employee list collection. So one would expect the result of this sequence equal operation to return true because both collections contain exactly the same data. Let's see what happens. Oh, and false is returned. The reason why false is returned is because we need to tell the compiler how to establish equality between objects of the relevant complex type, i.e. in this case, the employee type. So we achieved this in the previous video in this series by implementing the built-in iEquality comparer generic interface. So let's copy the relevant code for this that we implemented in the previous video in this series. Let's navigate to the GitHub repository at this URL that contains the code we created in the previous video in this series. Let's copy the class named Employee Comparer to our clipboards and paste the contents of our clipboards to our projects like this. We have red squiggly lines, so let's fix this by bringing in the appropriate using directive. So here we have implemented a class named Employee Comparer that implements the generic iEquality comparer interface that is strongly typed as employee. This gives us a way of telling the compiler how we want objects in our lists of type employee to be compared when determining equality between the relevant objects. So we are explicitly doing this here in the equals method, where we are comparing the ID, first name, and last name properties between two employee objects. We are returning true if the relevant properties of the relevant two objects are equal, and false is returned if any of the relevant properties of our two objects are not equal. Within the getHashCode method, we are returning the hash code of the ID property of the relevant employee objects. For more information on hash codes, please navigate to this URL. So now let's go to our main method, and we can pass in a new instance of the employee comparer class to an overloaded version of the sequence equal method. This object will tell the compiler explicitly how we want our employee objects to be compared. Let's run the code. And now the sequence equal operator works as expected. So note that we need to tell the compiler how we want objects that are defined as complex types to be compared when determining equality between the relevant objects. We can do this by creating a class that appropriately implements the I-equality comparer generic interface. Great! Let's move on to the concatenation operator named concat. We can use the concat operator to append one collection of data to another collection of data. So let's see the concat operator in action. Let's create a collection of integer values. Let's then create another collection of integer values. Let's append the second collection of integer values with the first collection of integer values using the concat operator. Let's write code to output the results of this concatenation operation to the screen. Let's run the code. Great! Let's do another example, but this time let's append a collection that contains a collection of objects of a complex type to another collection of objects of the same complex type. The complex type we'll use in this example will be our employee user-defined type. Once again, we can use the concat operator to achieve what we want here. Let's run the code. Great! Let's move on to the aggregate operators. Let's first look at the aggregate operator. Using the aggregate operator, we can perform a custom operation on values within a collection. Let's say we have a requirement where we need to provide a total for the annual salaries of our employee records. We also need to include the addition of an appropriate annual salary bonus in the final result. Let's say a manager gets a bonus of 4% and employees that aren't managers get a bonus of 2%. So let's say we have a use case where we need a result that is a total of all employee annual salaries, which must include each employee's bonus. We can take this added complexity into account when totaling up our employee annual salaries through the use of the aggregate operator. So the first argument is the seed value. So let's provide 0 for this argument. Using this argument, we are initializing the value that will be returned by our aggregate operator. The next argument is of a delegate type, where we can include the logic for our aggregation functionality in the form of a lambda expression. So as you can see in our logic for the relevant lambda expression argument, we are checking to see if the relevant employee is a manager, whereby we need to add a bonus of 4% to the relevant employee's annual salary. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee's annual salary. We can then include the appropriate bonus amount in our calculation. So we are adding up all employee annual salaries, which includes each employee's appropriate bonus. Let's run the code. Great! Say we want to output a comma-delimited string from our employee list collection. Each delimited item containing the employee full name, a dash, then the employee annual salary. Each annual salary must include the appropriate bonus. We also want to include a label preceding the comma-delimited string. We can achieve this using the aggregate operator like this. The first argument is the label, where an appropriate value could be something like employee annual salaries including bonus. Then the logic of our aggregation functionality can be expressed in a lambda expression for the second argument, like this. We can apply the same logic to include appropriate bonuses from our previous example. Let's run the code. Great, but we have a slight issue where a comma is presented at the end of our string. We don't want this comma in our final result. We can express this by passing a lambda expression as our third argument to an overloaded version of the aggregate operator. This argument allows us to perform a final operation on the results produced by the lambda expression passed in as the second argument. We first need to include another data type argument with an angle brackets following the aggregate method to declare the data type of the final output, i.e. provided by the lambda expression we are passing in to the last parameter of this overloaded version of the aggregate method. In the lambda expression passed in as our final argument, we are using the substring method to remove two characters from the end of the result, which means a comma and a space will be removed. This result is what we want. Excellent. So let's move on to the average aggregate operator. So to find the average annual salary for a list of employees, we can apply this code. Great. If we want to find the average salary for all employees in the technology department, we can use method chaining and the where operator to achieve this, like this. Great. For more information on method chaining, please view the second part of this video series. Let's move on to the count aggregate operator. So if we want to know how many employee records we have in our collection of employee records, we can apply the count operator like this. Great. If we want to know how many employees are members of the technology department, we can pass in a condition as an argument to the count operator. The condition that is passed in as an argument to the count method can be expressed in the form of a lambda expression. Great. Let's move on to the sum aggregate operator. So let's keep this simple. We just want the sum total of all annual salaries of all employee records stored in our employee list collection. We can apply the sum operator to achieve this. Great. Let's move on to the max aggregate operator. So if we want to return the highest annual salary property of all employee records stored in our employee list collection, we can apply the max aggregate operator in a LINQ query like this. Great! Let's move on to the generation operators, namely default if empty, empty, range, and repeat. Let's first look at the default if empty operator. So we can use the default if empty operator to return a new IEnumerable collection that when, for example, we apply the element at method on the new collection to check if the new collection is empty, the operation will return the default value for the relevant type used to strongly type the relevant collection. A query using, for example, the element at method against a collection returned from a default if empty operation will not throw an exception if the collection is empty. The default value of the type with which the relevant collection is strongly typed will instead be returned. For more information on default values for C# data types, please navigate to this URL. We'll see later how we can pass in a value to the default if empty method to specify our own default value that we'd prefer to be returned when, for example, the element at method is used to check if the relevant collection is empty, rather than the default C# value for the relevant data type. Let's look at an example using the default if empty method. So let's create an empty list of integer values. Let's perform a default if empty operation on this collection of integer values and assign the returned collection to a new collection of integer values. Let's use the element at operator and pass in 0 to the element at method to check if the collection is empty. you can see that the element at operator returns the default value for the integer data type, which is 0. This is an expected result. Let's create another example, but this time let's use the employee data type to strongly type our collections. As discussed, the default value for a reference type in C# is null. But as discussed, we can pass in a default value that we would prefer to be returned by, for example, the element at operator when the relevant collection is empty. So let's pass in an employee object where the ID property of the relevant employee object is set to 0. Null is not returned, as would be the case if we hadn't passed in a value to the default ifEmpty method, because we have specified our own default value where the ID property of the default employee object is 0. Great. Similarly, we could have set the default value for our integer collection example by, for example, passing in 999999 to the default ifEmpty method. Instead of returning the default C# value for an integer, which is 0, 999999 is returned. This is an expected result. Excellent. Right, let's look at the empty method. So we can use the empty method to generate a new empty collection. So for example, we want to create a new IEnumerable generic collection of employee records. We can do this by using the empty operator like this. Note, the empty method is not an extension method of IEnumerable or IQueryable like other LINQ methods. It is a static method included in the enumerable static class. So for example, we could instantiate a new empty generic list strongly typed with the employee user-defined type through the use of the empty method. We can then chain the toList conversion operator to this operation and return an empty generic list. We are using the toList operator to convert an IEnumerable generic collection that is strongly typed with the employee data type to a generic list that is strongly typed as employee. So for good measure, let's add a new employee item to our new list that we have generated through the use of the empty method and the use of the toList conversion operator. Let's write code to write the items, or in this case one item, stored in our new list to the screen. Great. Right, let's move on to the range generation operator. We can use the range operator to return a collection of values that are within a specified range. So let's clarify this with an example. We want to return a range of integer values in a collection where the first item in the range has a value of 25 and each subsequent item is incremented by a value of 1 until there are a total of 20 values in the relevant collection. We can achieve this by using the range method like this. In this example, the first argument specified is 25. This is the value of the first element, and the second argument specifies the number of elements to include in the relevant generated collection. When each item is added to the collection, it is incremented by a value of 1. So the second item will be 26, the third item will be 27, the fourth item will be 28, and so on. Let's run the code. Great. So using the range operator, we have generated a collection of integer values that fall within a specified range. Excellent. Let's say we want to generate a collection of a specified amount of elements where a value for each element in the collection is repeated. We can use the repeat operator for this purpose, like this. Great. Let's move on to the set operators, namely distinct, except, intersect, and union. Let's start with distinct. So let's say we have a strongly typed generic list that contains a list of integer values, some of which are repeating values. We want to perform a query against this list of integer values where we only want distinct values returned. We can achieve this by applying the distinct operator to our query like this. Great! Let's say that we have two collections of a specific type and we want to return elements with values in our first collection that are not equal to any of the values of the elements in our second collection. We can achieve this by using the except operator. Let's look at an example of using the except operator applied to two collections of integer values. So 1 and 2 are returned in our results collection because these values exist in our first collection and don't exist in the second collection. The values 3 and 4 exist in our first collection and also exist in our second collection. The values 5 and 6 exist in our second collection, and even though these items don't exist in our first collection, the except operator does not return these items as part of the results collection, because in this example, the except operator returns values that exist in the first collection and don't exist in the second collection. Let's try an example using complex types. Let's use our employee type. Let's create a generic list strongly typed as employee. Let's copy data that we know will exist within our employee list collection and add these items to the list we have named employee list 2. Let's add some additional items to the employee list 2 collection. Let's then call the except method on the employee list collection and pass in the employee list 2 collection as an argument to the except method. Then let's assign the results of this operation to an implicitly typed variable named results. We have of course used the var keyword to implicitly type our results variable. Let's write code to traverse the results and output the results to the screen. Let's run the code and see what happens. And this result is not expected. The output contains all items within the employee list collection. I would have expected that the items that were copied from the data class and added to the employee list 2 collection, as well as the other items that we added to the employee list collection, would be excluded from the results. The reason for the unexpected results is because we have not told the compiler how to compare employee objects when determining if one employee object is equal to another employee object. So how can we let the compiler know how we want one employee to be compared to another employee within our collections when determining equality between the two relevant objects? You may have guessed already how we can achieve this. We first need to create a class that implements the iEqualityComparer generic interface. We can then write code to establish how one employee object should be compared to another employee object when determining equality between the relevant objects. We have already included the code for this, which we applied when we created code to perform a sequence equal operation on two lists that were strongly typed as employee. So we have our class named EmployeeComparer that implements the iEqualityComparer generic interface. So we can reuse this class for our example that performs an accept operation on two generic lists that are strongly typed as employee. So all we need to do is create a new object of type employee comparer and pass this object into an overloaded version of the accept method like this. Let's run the code. Great! This is now an expected result. Let's move on to the intersect operator. So we can use the intersect set operator to return a collection containing only those items that exist in the employee list collection that are equal to the items that exist within the employee list 2 collection. And now that we know we are comparing elements in two collections that are strongly typed with the employee complex type, we need to pass in a new object of the employee comparer type, i.e. a type that appropriately implements the generic iEquality comparer interface. This tells the compiler how to compare two objects of type employee when determining if the relevant employee objects are equal. Let's run the code. And this is an expected result. Great. Let's move on to the union operator. The union extension method requires two collections and returns a new collection that includes distinct elements from both the collections. We can again use the same data we have used in the previous two examples to test the union operator. Right, let's write the code for this. You will notice we are also passing in an object of type employee comparer to the union method. Let's test the code. Great! So let's see what happens in this example when we don't pass in an object of type employee comparer to the union method. You can see that duplicate records are included in the results as a consequence of not passing in an object derived from a class that appropriately implements the generic iEquality comparer interface. And of course, we know we have already created such a class. So let's ensure that we pass in our object of type employee comparer to the union method so that only distinct employee objects are included within our results. Excellent. So let's move on to the partitioning operators. These partitioning operators include the skip, skip while, take, and take while operators. Let's first look at the skip operator. Use the skip operator to skip over a given number of elements in a sequence and then return the remainder. So let's query our employee list collection using the skip operator. Let's skip over 2 of the elements stored in our employee list collection and return the remainder of the elements using the skip operator. Great, this is an expected result. Let's look at the skip while operator. Using the skip while operator bypasses elements in a sequence as long as a specified condition is true, and then returns the remaining elements. Let's see this operator in action. So the condition here is skip elements in our sequence of employee objects in the employee list collection while the relevant employee object's annual salaries are above 50,000. Great, this is an expected result. Just to make things a little bit more clear on how this operator works, let's add a new employee record to the employee list collection. This employee record has an annual salary of 100,000, which of course is above 50,000. Let's run the code. And you can see that while the condition is true, the items in the relevant collection are skipped, i.e. will not be returned from the query. However, all subsequent elements in the sequence will be returned once the condition returns false. Even though the last element in the relevant sequence has an annual salary property greater than 50,000, it is still returned, because the third element in the sequence caused the condition to return false. The fact that the last element has an annual salary above 50,000 and therefore causes the condition to be true doesn't mean that the last item will be returned by our query. Note that once the condition returns false, all items from that point will be returned from our query. Right, let's move on to the take partition operator. The take operator is used to return a specified number of contiguous elements from the start of a sequence. Let's see this operator in action. This is an expected result. Great! The first two elements in the relevant sequence of elements in our employee list collection are returned by our query. So let's move on to the take while partitioning operator. The take while operator returns elements from a sequence as long as a specified condition is true, and then skips the remaining elements. So let's use the same condition that we used in the skip while operator example. So here we are using the take while operator to return elements from the relevant sequence that have an annual salary above 50,000. So the first two elements in the sequence are returned by our query. As soon as the third element is evaluated and the condition returns false, the elements from that point onwards in the relevant sequence will not be returned by our query. So for example, the fact that the fifth element in the employee list collection has an annual salary property that is greater than 50,000 is irrelevant, because when the third element causes the condition to return false, and in terms of the take while operator this means that from that point onwards, the rest of the elements in the relevant sequence will not be returned by our query. Great! Let's look at the conversion operators toList, toDictionary, and toArray. So let's look at the toList conversion operator. A query written in query syntax will return an IEnumerable collection containing the results of the query. What if we need our results to be returned as a generic list? We can achieve this using the toList conversion operator. Let's create an example to clarify this point. So for this example, let's query our employee list collection for employee records that have an annual salary property greater than 50,000 using query syntax. Note the red squiggly lines here. This is because we are attempting to assign an IEnumerable collection to a variable of type generic list. The compiler is telling us that we have created a type mismatch. So we can use the toList operator to convert the IEnumerable